let me say a little bit more about radioactive decay. There's at least there's one problem in the homework, and we're going to do a lot more about it later. In class, what I started out with was this fanciful idea that all the atoms in some radioactive substance are continually flipping coins or rolling dice and deciding whether to spit off a particle and change into something else, and therefore decrease the amount of the substance. It's not exactly how it works, but that's functionally what happens. It amounts to what happens. It's this random process, but that ends up giving a very predictable answer. And one of the simplest example is if every 1 year half of the substance goes away. Basically changes into something else. And if we only care about the amount of the particular substance, we can just say it's going away. What does that look like? Well, let's make a little table here. So let's say A is the amount of the substance. Let's say we start out time t equals 0 with, let's say, 16 kilograms. Then time 1, half, after 1 year, half of that substance has disappeared, and we're down to 8 kilograms. Now, it's very easy, even if you really are paying attention, once your mind wanders on a test, it's very, very easy to slip back into the model of linear functions. Linear functions are wonderful. They model lots of things, but not this. And you're going to want to watch out for the error that amounts to saying, okay, if it went from 16 to 8 in the first year, then that 8 is all going to be gone, and after 2 years, it's going to be there's going to be nothing. But the way it works is that all the atoms in that 8 kilograms, they roll their die again, or they flip their coin again. Only half of them are going to come up heads. There's going to be plenty of them that came up tails this time and didn't die, and came up tails this time and don't die. And so half of them are going to be around the next time. After 3 years, it's going to be 2 kilograms. After 4 years, it's going to be 1 kilogram. After 5 years, it's going to be 1/2 of a kilogram, etc. Well, that's exactly an exponential function. Let's see what models that. Looks like A of t is 1/2 to the t. So that's a very simple example, a simple model of radioactive decay. We say in this case that the half-life of the substance is equal to 1 year. Because every year 1/2 of it decays compared to what was at the start of that year. So let me compare that. Well, let's do another example that's similar but just a little bit changed. Let's change it to every 100 years, half of the substance goes away. And let's say it starts with, oh, I forgot the 16. Hopefully people notice that. This is 16 times 1/2 to the t, because when t equals 0, that's going to give you 1, it's going to be 16. When t equals 1, it's going to be 16 times 1/2, then 16 times 1/4. So that 16 should be in there. Sorry, guys. So let's say every 100 years, half the substance goes away. Let's say we still start with 16 kilograms. So t equals 0, we got 16 kilograms. Well, how long does it take to get to 8 kilograms? Well, that's 100 years now. After 200 years, that's another 100 years. They've had enough time to flip their coins, and half of them spit out a little particle and change into something else. They go away. Every 100 years now, we have this same process. So now how's this function going to change? It still starts with 16, and then 1/2, well, it's still multiplying by 1/2 each time, but I've got to change the t here, because that is much, much quicker. That was what happens if it did it every year. Well, what's going to happen is that I want the exponent to be 1 when t is 100. Because exponent 1, if I end up with a 1 in here, that's going to give me 16 times 1/2. That's the right answer. So when t is equal to 100, I want this quantity to be a 1. Well, if I take t over 100, that's going to work. And let's test that. If t equals 200, then 200 over 100 is going to be 2, and that's going to be 16 times 1/2 squared. Okay, that's going to be 4. One way to see that is to do some graphing. let's graph 16 times 1/2 to the t and that really shouldn't be that hard for it to do. Okay, there's 16 times 1/2 to the t. It plotted it for negative values, so let's plot it. Let's just change the plot here a little bit. Let's take that from 0 to like, well, 0 to 6, say. I don't know why it ends up so big. Oh, because I've got the magnification on. Okay. So here is that starting at 16 and going down, down, down in 6 years. Well, let's also plot 16 times 1/2 to the t over 100. Yeah, no, that's going to work. I don't need parentheses there. It's smart enough to do that. And also from 0 to 6. What's going to happen? That's weird. It looks like a straight line. Think about that for a second as to why it might look like a straight line. What should this do? If I take this graph that had this shape and then I change t to t over 100, well, what that should do is make this much, much wider, 100 times wider. So in fact, the 6 here, of course, is a very unrealistic domain now. So in fact, what I need to do is change the variable. Let's go to 600 now. And let's see. Yeah, okay. So now that's that old graph right here. In very short span of time, in terms of this 100-year time scale, that is going to a very small amount. But now this guy is taking 600 years to do what the other thing did in 6 years. Go down, down, down to a very small number. Now notice, this may look like it's going to 0, but it's not equal to 0. These things are never going to exactly equal 0. And that's true about radioactive decay. If you just leave something alone, it's going to take an incredible amount of time for it to all go away, because you're starting out with an immense number of atoms, like 10 to the 23rd atoms. It's going to take a long time for those all to end up going away. So here, the half-life has turned into 100 years in our new example. And we've got something where, if you look at the graph, you go out 100 years, you notice it's exactly half, 8, of what it started with. So if you're looking at an exponential decay graph, it's not too hard to find the half-life. Just pick any 2 points whose heights are one height is half the other, like 8 and 16, and see how far apart they are on the time axis. Now, here's the other thing I wanted to say, which is, well, let's see. Let's see, it's not going to work for that. Not really. Here's a problem. Here's the start of the problem you're going to be doing. Radioactive decay. I think it's 65. M of t equals, and something that looks a little different. E to the minus 0.015 t. There's an e in there. Hey, what the heck is the e doing in there? Well, I started out by looking at 1/2. But that was a very specific example. It was something that wanted to focus on this idea of a half-life. It happened to be that the half-life was really simple for both these examples, and I could describe it as 1/2 to a power. And notice it was 1/2 to either t or t times a positive number. Here it's you could write this as 0.01. Oops. 0.01 times t is another way to write that. So it's a number smaller than 1 raised to a positive number times t. Now, they're claiming, in the book, they're claiming that you can describe radioactive decay by e, which is a number bigger than 1, to a negative number times t. And there's the 1/2 doesn't appear anywhere here. Well, let's go ahead and graph this and see. I'm not going to give too much away from the problem. Let's go ahead and graph this and see if it's plausible. Oh, looks like a straight line. Well, you know what? Again, we're looking at way too little of this graph. Let's zoom out to see if we can see a little better. Let's start at 0, and let's go to 100, say. Okay, now it's looking a little more plausible. It's a little misleading because that's not going down to 0. Let me change the view here so that y actually does go down to 0. Okay, so now this does look like a kind of exponential decay curve. So it's plausible, and let's see what's happening. An e to the positive number times t would be increasing. The negative flips it left-right, so it does turn it into a decaying exponential. The question that we're going to have to ask, we're going to have to answer pretty soon, but we won't be able to do this quite yet until we have some understanding of logarithms and how to solve equations involving exponentials, is how could I relate this kind of expression? Could I write that in a way that's more like this, that makes it more clear what the half-life is? And that's going to be an interesting question. But the thing I just wanted to get across right now is that, yes, this is another alternate way of describing radioactive decay, and we're going to soon have the ability to relate it to the half-life story. But right now, we just want to take it on faith that this is a good model and answer the questions that are natural to answer based on this kind of function.